the moon is to become a huge laboratory to detect hidden waves from supermassive black holes. The moon could soon be turned into a giant experiment for detecting a presently hidden band of gravitational waves of the frequency generated by collisions between supermassive black holes. According to what scientists are revealing, gravitational waves are ripples in the fabric of space-time that are created by accelerating masses, and they spread out from their points of origin at the speed of light. They were first predicted in the early 1900s by the French mathematician Henri Poincaré and the German-born theoretical physicist Albert Einstein. They recently come into their own as a way of astronomers to probe spectacles invisible to electromagnetic observatories. In particular, they can open a window to some of the cosmos's most violent phenomena, from supernovas to merging black holes and even the universe's origins in the Big Bang. There are a number of gravitational wave detectors presently in operation, arguably the most prominent being those in the LIGO-Virgo-CAGRA collaboration, which comprises 3 laser interferometers based in the US, Italy, and Japan, respectively. These detectors work by using twin lasers to measure even the tiniest changes in distances, and they're capable of detecting gravitational waves with frequencies in the range of 1 to 1,000 hertz. In contrast, an alternative approach works by measuring subtle variations in the periodic signals received from pulsars, spinning neutron stars, and emit beams of radio waves in a manner not dissimilar to the rotating beacons of a lighthouse. This setup is capable of detecting lower frequency gravitational waves in the nanohertz range, as are caused, for example, by the merging of supermassive black holes. This means that together, current detectors have a sizable blind spot across the microhertz range, which lies between those 2 frequency bands. Therefore, they are incapable of detecting the kind of gravitational waves that physicists expect to generate as pairs of supermassive black holes orbit each other in the final stages before they collide. Theoretical physicist Dr. Alexander Jenkins of University College London and his colleague Dr. Diego Blas of the Autonomous University of Barcelona, Spain, are, as the former puts it, aiming to fill this gap. And to do this, Dr. Jenkins explains they propose to build on an idea that dates back to the 1970s and measure how gravitational waves influence the orbits of binary systems, including the Earth-Moon systems. According to the duo, gravitational waves that buffet the Earth and the Moon in the microhertz frequency range, that is around 1 oscillation every few weeks, should have a subtle but detectable influence on the pair's orbit. For the hypothetical and very simplistic example, a continuous gravitational wave with the same frequency as the Earth-Moon orbital motion might nudge the Moon a bit closer to Earth at each cycle thanks to resonant phenomena. This minuscule change in the orbital patterns would be imperceptible to us and nothing to worry about, as the Moon has been drifting away at a much greater rate from our Earth, presently around 1.5 inches every single year, for billions of years as a result of interaction with Earth's tides. Even though gravitational waves are not going to drop the Moon on our heads, however, measuring the subtle changes in the Moon's orbit using laser ranging could reveal the presence of previously undetectable microhertz gravitational waves. Laser ranging works by bouncing a beam of concentrated light off of one of the special reflectors left on the lunar surface by the US Apollo and Soviet Lunokhod missions and measuring how long the signal takes to come back. In their paper, Dr. Jenkins and Blas showed that such studies of the Earth-Moon system could be used to allow physicists to set a new, refined upper bound on the strength of gravitational waves in the microhertz gap. And as if treated the Earth and the Moon as a giant piece of lab equipment was not grand enough, the researchers say they want to explore taking the core principle even further Dr. Jenkins said it's not just individual binary systems. We also need to see how entire galaxies respond to gravitational waves. Physicist Victor Cardoso of the University of Lisbon, who was not involved in the study, said that the idea was an exciting and novel way of seeing gravitational waves, and he said the idea is simple, but it requires difficult calculations to implement and show that it works. Filling the detection frequency gap, he said, may reveal unexpected new sources of gravitational waves. Experts may find, he said, that the universe is full of mysterious gravitational wave content. And the full findings of the study were published in the journal Physical Review Letters. And this is on today's article in Express UK by Ian Randall. Please leave your comments. Thank you for your support. Finally, support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.